In this video, we are going to look at a cipher called the shift cipher. It is also called the Caesar cipher. First thing we're going to do is review the mod operator from one of our math videos from before. We're then going to talk about using numbers to represent characters. Next, we're going to use the mod operator to define what the shift cipher is. And then finally, we're going to do a sample encryption and then a sample decryption as well. Alright, so remember about the mod operator. We have a and n are integers, where n is a positive integer. Then we say that a mod n is the remainder that you get when you divide n into a, or looked at from another perspective, you can think of it as the remainder you get when you divide a by n. Now, if we look at the quotient remainder theorem version of this, it says that if you have a equals nq plus r, where q is the quotient, r is the remainder, that means your a mod n is going to equal r. And actually, if you flip this equation around, subtract nq from both sides, and look at it from the perspective of r, what you have is r is equal to a minus nq, which means that you can get to r from a by adding or subtracting a multiple of n. Now, it looks like you're just subtracting, but if you let q be a negative number, that will actually add multiples of n. So you can think of it as either adding or subtracting a multiple of n, and that will be useful to us in a little bit. Alright, so one of the things that happens in our ciphers is we would like to use some number operations to help us develop some ciphers. In order to do that, we have to find a way of representing our characters, which are letters and don't have an intrinsic mathematical value, and use numbers to represent them. So there's a couple ways we can do this. One way is the ASCII way of doing it, and that's a way of representing all characters that you'd see, say, in your computer, on your computer keyboard, and in different computer operations. We're going to stick to a little more simple system. What we're going to do is we're going to start with representing A with the number 0, and then go in alphabetical order and just go up one each time. So B gets represented by 1, C is represented by 2, all the way up to Z, which will be represented by 25. If you start at 0 and end at 25, that gives you 26 letters. So, for instance, if you wanted to represent the word hello with numbers, the H, if you look at the H, that's a 7. If you look at E, that's a 4. The two L's are each going to be 11. And then the O is going to be 14. Right? So that's how you'd represent the word hello. Now, I just want to, even though we're using some kind of encoding to go from letters to numbers, this isn't really a cipher or code. This isn't something that's secret, right? This is just a way we take letters and represent them as numbers. So we're not done ciphering yet. All right, so now I think we're ready to define the shift cipher. And again, I mentioned before, that's also called the Caesar cipher. So here's how we start. The first thing I got to tell you is what the key is, and the key is just going to be some number between 1 and 25, and for the purposes of describing this, I'm just going to call that key little k. Okay. So what you're going to do is first take your plain text and take each letter in that plain text and convert it into a number as in the previous slide. So if you have it, wherever you have an A in the plain text, that'll be written as a 0. Wherever you have a B, that'll be written as a 1, etc. Then what you're going to do to each of those numbers is add k to each of those numbers. Now that can be problematic if you get a number that's bigger than 25, so to make it so that it's between 0 and 25, you're going to compute that number mod 26. So if you have a number x, you just compute x plus k mod 26. Then what you're going to do is replace each of those numbers with the letter that corresponds to it in the chart that we had before. So if you had a number 3, for instance, you'd replace that with the letter D because 3 corresponds to D when we're representing letters by numbers. And that will become your ciphertext. So let's see how this works in a couple of examples. The first example we're going to use is a shift cipher with key 12. What that means is when we convert everything into numbers, we're going to add 12 to encrypt it. So the plain text we're going to use is her name is Rio. And what we're going to do first is we're going to convert everything to numbers. So we look at the H. The H corresponds to 7. The E corresponds to 4. The R corresponds to 17. And we keep doing that with all the other letters. Now, I put them all in parentheses to show you where the words are. But, of course, when we write this as numbers, we're going to get rid of those parentheses and just smush them all together. The next thing we're going to do is add 12 because that's our key. And when we do that, we get a bunch of numbers, right? Notice that some of them are bigger than 25, which means we have to find their mod to figure out what letter they correspond to in the ciphertext. But the first couple are actually going to be fine, right? 19 and 16, if we take those mod 26, that's just 19 and 16. 29 is going to be a little trickier. Now remember, we can add or subtract a multiple of 26. If we subtract 26, we end up with 3. So that's nice. That's between 1 and 25, or 0 and 25. 25, 12, 24, 16, and 20 are all fine. But notice the next one is 30, which is bigger than 26. So we're going to subtract 26 from that one to get 4. 29, we have the same issue. We got to subtract 26 from that one to get 3. And then 20 is fine. And then 26, we have to subtract 26 to give us 0. Now, those are the numbers that are going to represent the letters of our ciphertext. And when we put when we consult the chart to convert those into letters, we end up with T, Q, D, Z, M, Y, Q, U, E, C, U, A. Okay, so there's our ciphertext. Now, when we do decryption, it's pretty much going to be the same. It's just that we have to do everything in reverse. So I'll use a different key in this one. We'll use a key of 8. So the first thing we're going to do is look at our ciphertext, right? And if we're working backwards, what happens in the last step that when we go from numbers to ciphertext is we take those numbers from the chart and convert them to ciphertext. We're going to do that backwards since we're decrypting. So we're going to convert those all to numbers. And when you do that, these are the numbers that you get. So you look at A, that's a 0, an I, that's an 8, a D, that's a 3, and so on down the line to Z, which is a 25. Now, those, of course, aren't going to be the numbers that correspond to our plain text. What we have to do is use the shift cipher, use the key to figure it out. Now, when we encrypt the plain text, we add 8 to each of the numbers, which means when we decrypt the ciphertext, we have to subtract 8. So what we're going to do is subtract 8 from each of those numbers. Here's what we get. And very similar to what happened when we were encrypting, we're going to get a lot of numbers that don't make sense. Look at all those negative numbers that don't correspond to any numbers at all. But remember, we can always get to the right one by either adding or subtracting a multiple of 26. And in this case, adding 26 to those is going to be the thing we want to do. So when we add 26 to that negative 8, we're going to end up with 18. The 0 is fine. We're going to have to add 26 to that negative 5 to get 21. The 4, 0, 5, 17, and the other 0 are all fine. The next one is a negative 2, which we're going to have to add 26 to get 24. And then the 4 and 17 are fine. And that means we can take all those numbers and convert them into letters using our chart now. And when we do that, we end up with this conglomeration of letters. And if we separate those out into words, we end up with save a prayer. All right, so now having seen all that, I think you're ready for the in-class activities. Look for the one that's called Shift Cipher.